Hello. Windows file servers, the performance is mostly self-tuning. You don't have to worry too much about changing a lot of parameters. Thank you very much. Enjoy TechEd. Okay, yeah, I really wish that's the talk I could give. And actually, for the most part, Windows performance and Windows file server performance is self-tuning. But if it really was, and if there was no problems that you would ever run into, then, well, I wouldn't have to be up here giving this type of talk. Now, what I'm going to try to cover today is I'm going to walk you through the basics of everything that has to come together and work together to give you an efficient and well-performant file server. Because when it comes to performance in file servers, it's really not about, you think of performance, you think things going faster. It's not about going faster. I mean, those little electrons, there's a limit to how fast they can go, and they're already going as fast as they can. It's all about efficiency. It's all about making sure that the data that you want to access is available as close to you and where you can get to it as efficiently as possible. So I'm going to be making sure that you understand the high-level components, how they interact, how they will be, or how you can configure them to be the most efficient as possible. But before I tell you any of that, I do want to make sure that you understand that a file server is, for the most part, self-tuning. And that if you start messing with some of the parameters that I'll be telling you about later, you are, in a sense, playing with fire. And that's why, before I give you any real content at all, you all must take the solemn oath. Please raise your right hand and repeat after me. I state your name. Okay, I'm the one who's supposed to be telling the jokes. Do solemnly swear that I will never ever, never, ever, ever, never, never, ever, never, never, ever, never, 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 ever. Come on, try it. Okay, good enough. Play with any performance parameters without testing them first. You didn't say that with conviction. Say it again. Play with any performance parameters without testing them first. Okay, good enough. All right. I'm serious about that. We'll be talking about some of the things that affect some of the guts of how things interact. Don't change anything without testing it first. Now, sort of as an overview and to kick things off, at the end of this, I want you to be able to understand this graph, understand what has changed and what has let us get to some of these performance numbers that we've talked about in press releases, etc. What this graph is trying to tell you, this is what we talk about whenever we talk about file server performance. The one benchmark we have that's an industry standard that everyone understands is NetBench. So I want you to know when you see graphs like this and we start talking about performance increases that we're talking about the performance of the NetBench benchmark. And what that is measuring is all about throughput. When we talk about performance, there are several different variables that we can be talking about. We can be measuring latency. That's when I issue a request, how long does it take for me to get a response back? Or we can talk about throughput. When I issue lots of responses, how much I/O can I sustain? NetBench is all about measuring throughput. And as you have seen, we've done quite a bit of work between Windows NT 4.0 and Windows Server 2003 to increase the throughput that a file server can sustain. You'll also notice that as you increase the number of processors on the system, that the relative percentage improvement increases on Windows Server 2003. Basically what's been going on and where we've been having a lot of our innovations and gaining a lot of our performance benefits is we're being more efficient in how we're doing our network accesses, and we've also made lots of changes in the core operating system kernel itself to improve scalability as you increase the number of processors. Now back in the NT4 time frame, 8 processor machines were exceedingly expensive. Now they're becoming more common, so this work is going to start paying off. So you're seeing both a combination of better software and its increased ability to take advantage of better hardware, leading to overall better performance. Actually, I think this next graph explains things a little better as sort of a motivating factor. We're showing two things here. As you move from the left and go over to the right on the graph, we're changing both the software on the system and the hardware that's running on it, where we're going from hardware that was available around the time that NT4 shipped to hardware that is available now with Windows Server 2003, and we're also upgrading the software at each step along the way. And the blue bar is the NetBench throughput. The red line is trying to map that to something that makes sense to your business. How many servers do you need to support a fixed number of users? So what you've seen is that back in the NT4 timeframe, to support 40,000 users, you probably needed around 100 file servers. With the performance that you can get out of today's hardware and out of today's software, you can support that same number of users with 8 servers. So if you're trying to put as many people, as many home directories, as many project shares, etc., on a file server as you can, what are some of the things that you need to consider? What I'm going to do is I'm going to walk you through the various levels of the software stack, starting with a client that's going to be trying to request data from a server, and I'm going to walk through each of the things along the way. And if I do my job well, when you walk out of here, you'll walk out with a better understanding of how these things work so that you can understand better some of the performance characteristics and performance tuning. So let's start with the network stack. I've got a client, and that client is trying to request data from a server. Most likely, you're going to be using the SMB protocol. The SMB protocol was originally developed back in the Windows NT 4.0, actually no, in the Landman days, long before Windows NT 4.0. And some of the basics about it is the protocol is a stateful protocol. Now by that it means that when a client connects to a server to start reading some data, the server has to remember information about every client that is connected to it. Now that has some advantages and that has some drawbacks. Some of the advantages are it lets us do much more performant operations like streaming data because the server can remember the last offset in the file that the client has read. It also lets us issue some long-standing operations like change notifications. The client can issue a request over to the server and say, let me know if anything changes in this directory. And in order for an operation like that to work, you have to have some sort of state that's kept around on the server. So those are the advantages of that design. Now, the drawback of a stateful design is that it does have an impact on the file server scalability because it has to remember information about every client that's connecting to it. And we'll talk a little bit more about that in a little bit. But the first little performance optimization that I want to tell you about when you're dealing with file servers and when you're dealing with things coming in over the SMB protocol is op blocks. Now, before I came here to give this talk, I did some research on the net, typed op blocks into Google to see what sort of information was out there. And what I learned is that there's a lot of misinformation and a lot of misunderstanding about what op blocks are and how they affect performance. So this is going to be our first little, in a way, a little computer science lesson of the internals of the SMB protocol and how op blocks work. Now think for a moment. I'm going to start walking through, by the way, as I'm not just standing up here and walking around strictly at random. What I'm going to be doing is over here, when I'm over here, I'm going to be talking about components that are on the client. And as I start moving over, I'm going to move over into the server, and then I'm going to move down into the file system, if I can stay out of my own slides. And then I'm going to move down into the disk stack, etc. So as you start seeing me walk across the front of the stage, try to remember in your mind what part of the operating system I'm going to be talking about. So I'm over here on the client. There's some data way over there on the disk that I want to be able to get. Now, we talked about before that performance is not about speed. If it was about speed, then all I would do if I wanted to get data over on that disk is run over as fast as I can, read my data, Is this on? Can you hear me? If I want to access that data that's on the disk, I want to have a copy of that data that's close to me. So then when I want to read the data, I just casually walk over here. Ideally, I don't even cross this chasm over to the server. I want to have a copy of the data here with me on the client where I can read it and manipulate it. Now the problem is when you're dealing with a file server and you're dealing with lots of clients that connect to it, if I keep a copy of the data here and I start writing it, if there's another client somewhere else that's trying to read that same information, they don't get to see what I've written. So that's what op locks are all about. It's a method to let us know when it's safe to keep copies of the data on the client and manipulate them close by, and when we have to go to the server, cross this chasm of the network to manipulate the data. Now here's how it works. When I'm on the client and I open a file, the very first thing I have to do is I do have to initiate a network connection over to the server. Over on the server, it opens the file, and then it looks to see, has anyone else opened the same file? And if so, what sort of access have they been requesting of that? If no one else has opened the same file, when the server responds back, he'll say, you now have an open handle to the file, and by the way, you have an exclusive, or what we call internally in Microsoft, a batch op lock. What that means is it's a guarantee to the client that nobody else is trying to read or write that same data. So what I can do on the client then is I can read the data over and keep a copy locally, and I can manipulate that copy locally. I can both read it and I can write it. And not have to tell the server about it because nobody else cares about the data aside from me. Now, if someone else comes along and tries to read that data then, what happens is what we call an op lock break. The first client had a copy of the data, had a copy locally on his machine, was doing all of these operations cached. When the other person comes along, says, I want to read that file, the server remembers, hey, there was some other client. Here we're getting to that part of how SMB is a stateful protocol. The server had to remember that there was someone else who was reading that file and had that information cached. He sends along the op lock break notification to the client, and then the client says, okay, I've been writing some data to this. I'm going to go ahead and I'm going to flush it back to the server. And that way, from then on, the two machines see the same copies of the data because at the very least, they're crossing the chasm over to the server. So all writes start going to the server, all reads start going to the server. And that's what happens when an op lock is completely broken. There's one other stage of an op lock called a level 2 op lock. Our naming internally is completely inconsistent. You get some batch op lock, level 2 op lock. I don't know why we came up with those names. But what a level 2 op lock means is that there are lots of readers and no writers of that file. If you get a level 2 op lock, it means that you can read that data in from the server and then keep a copy with you. And you can keep satisfying additional reads from your own copy because nobody's changing it. As soon as that writer comes in, however, then you have to break that level 2 op lock, and all reads and all writes are going over to the server. So op locks are a key thing to balance both performance by letting me keep a copy of the data close to the application that needs it, and consistency. It lets me do these performance optimizations, but still detect if someone else is trying to access the same data, and therefore we need to start communicating through the server. Now, the reason why I went through that long explanation is I found information out on Google where they were talking about how, op locks can actually lead to performance problems, and the easiest way to get rid of those performance problems is to turn off op locks. There is, in fact, a registry key where you can turn off op locks. And even though I made you all take an oath not to mess with performance settings without testing first, this is one I won't even tell you where that registry key is, because you don't want to turn off op locks. Every now and then, when there is a performance issue with an op lock, it's most likely a bug. We fixed the bug. You want to keep on using op blocks. The bug would be, by the way, that if a client has gotten an op block, I'm reading and writing the data and I'm keeping all the information on my client, and another client is trying to issue a read. So I go over here and I issue an op block break to that original client to tell it to flush data. If that other client is misbehaving, if it has a bug, we'll wait up to 25 seconds for him to acknowledge the op block break before we realize that client's probably dead or misbehaving. And that's the type of area where there can be problems where op blocks are introduced. But you almost never, ever, ever want to be changing that particular parameter. It's a very important optimization for file server performance. And in cases where you find that something is wrong with an op block, then it's probably a bug that we at Microsoft need to fix, not something where you want to start running day-to-day with op blocks off. Now, there are a couple of other performance considerations, and I've got the KB article numbers up there. Things where you might, in certain circumstances, want to intervene in the self-tuning that a file server does. Both of these apply to, they're settings that apply on the server side, so things that you would do over here. Now, the first one has to do with server connection pre-allocation. Has anybody run into server, it's either 2021 or 2022 errors on your file servers? Yeah, a couple of you have run into this. Let me explain what that means, and this KB article tells you about what you can do to fix that. Deep inside the Windows NT kernel, the rules for programming are incredibly complex. It has to do with the fact that the Windows NT kernel is pageable for the most part. So parts of the operating system kernel itself can be paged out to disk, and fully preemptible. You can be doing work at any time and be interrupted by the hardware. And as a result, there are some programming rules that you have to follow. So for instance, when the server receives a request to initiate a network connection, to establish that connection, to start remembering some state, it has to have memory where it can remember that state. And one of the rules of programming in the kernel is when you're interrupted by the hardware to say, please initiate a network connection, you can't actually allocate that memory structure. It would violate one of the rules of programming. It could be generating a page fault that couldn't be satisfied because we've already been interrupted by hardware. So we have to have a stash of those connection objects already allocated, waiting for us to start using them. If you start getting server 2021 or 2022 errors, what it means is we can't keep that stash of connection memory structures around. That we're getting more network connections coming in, and they're coming in faster than another thread in the kernel can replenish those connection structures and allocate them. So what this knowledge base article will tell you how to do is how to change some settings in the registry so that you can have a larger pool of those connection structures lying around. If you take the recommended maximum settings for those two registry keys, then every customer we've talked to who's been getting 2021 or 2022 errors, they go away. It places a higher cost on kernel memory because you're keeping additional data structures around that you might not need all of the time, but it does completely get rid of those errors. Oh, and by the way, I've been talking about server 2021 or 2022 errors. What that means in the real world is that some client over here was requesting a connection to the server, and the server denied it because it couldn't allocate the structure. So what it will appear to you as a network administrator is that there are clients who can't connect to the server temporarily. If they try again, the connection will succeed. The next KB article has to do with another, I can't remember the event ID number, but it's an error where the server can't allocate one of its data structures out of paged pool. Now, the problem there comes with paged pool, and we'll talk about it a little bit later in more detail, is one of the key areas of kernel memory for a file server. The paged pool is just a place in kernel memory where anything that's operating in the operating system kernel can request arbitrary data structures of arbitrary size. And by paged, it means that those data structures can be paged out to disk if we're starting to get pressure on our physical memory. It's a very key resource for us for a file server. And what happens in some cases is, in particular, the memory manager is keeping data structures around about all of those files that are open. And that's something that it can start trimming. If it starts realizing that there's memory pressure, it can start freeing up some of those data structures. But what might happen is, if it can't free them up fast enough, then the SMB server can't allocate some of its data structures. And once again, what happens is, as an administrator, it appears that clients can't open files on the server temporarily, but they can try again and things succeed. And we log an error when those happen. This last KB article, what it tells you can do, there are two things that you can possibly set. One is a parameter that the memory manager uses to determine when it needs to start freeing up some of its data structures. By default, if the paged pool is 80% full, then the memory manager starts freeing up its data structures. The KB recommendation, if and only if you start having this problem, is to tweak that down maybe to something like 40%. So that causes the memory manager to start more aggressively purging its data structures. The second thing that you can think of doing is increasing the paged pool size instead of accepting the default that's given in the operating system kernel. But wait for a couple of slides more before you consider that as an option, as something that you can do in this case. So at this point, we've talked about a lot of the key things that are involved with getting data all the way over there from the disk, having to do with what's happening between the client and the server itself. Once you get over to the server, so I'm over here now, trying to duck so I don't block my slides, I need to issue requests back out to the client. I need to satisfy those data requests. How am I going to do it? I'm still pretty far away from that disk over there. Things will be more efficient if I can serve that data up from my server memory. And this actually is probably one of the key things about having good file server performance, is it's all about having efficient caching. Now, I'm going to do another. This is the second big computer science digression in this talk. Understanding caching in the Windows NT architecture is actually surprisingly complicated. There are three components that interact together to give you the file system cache. The memory manager, the cache manager, and the file system. By the way, if you want to, you go back from TechEd and you want to increase your, Microsoft street cred, you call the first one, you call it MM, the second one CC, then you've got the lingo down. Capital M, lowercase m, capital C, lowercase c. Internally, that's what we call those components. MM, CC, and the file system cooperate to give you the file server cache. Now, I actually know very well the developer of the cache manager, and I said, I'm going to try to explain to people how these things interact. And her response was, good luck. It is pretty complicated, but you guys are a pretty smart audience. You can probably keep up with it. Here we go. Here's the first thing you have to know to understand caching in Windows NT. This is very, very important. If the rest of this little explanation goes over your head, just remember this one thing. The Windows NT cache is implemented in the kernel mode virtual memory. Now, here's what that means in more plain English. If you remember from some of the basics of computer science, everything since, I forget the operating system, has implemented a virtual memory system. And what that means is your 32-bit memory address doesn't actually refer to a real address in the memory of your computer, but it's a virtual address. It's just a lookup into another table that tells you where to go in the computer memory to get the object. And the cache manager implements its cache in virtual memory, in a virtual address. Now, the other thing to know about how Windows NT manages virtual memory, all virtual addresses on our 32-bit operating systems are 32 bits long. And what we do in Windows is we divide those 32 bits, that 32-bit address space, in half. 32 bits, by the way, if you haven't been hanging around with enough computer science geeks, that's enough to address 4 gigabytes of memory. So if we divide it in half and give half to the kernel, it means that the kernel address space in the operating system is 2 gigabytes. And then any other application that you run can get 2 gigabytes of its own. Now here's sort of the weird thing about how that works. If you're running multiple user mode applications on your machine, and if you have more than 4 gigabytes of memory, what we can do in the operating system is sort of divide up and give SQL Server its own 2 gigabytes of memory, and some other application that you would run on that machine its own 2 gigabytes of memory. And we can start, dividing it out and taking advantage of all of that physical memory on your machine. But the kernel has a flat, fixed 2 gigabyte address space for the entire machine. It doesn't matter how much physical RAM you've put in. If this is a huge honking machine, you had a lot of capital budget left over at the end of the year, so you wanted to buy something big and you put 8 gigabytes of RAM in it, the operating system itself can only use 2 gigabytes of that. The remaining 6 gigabytes could be used by user mode applications, but not by the operating system. So the cache manager, what CC does, is it takes some of that 2 gigabytes of address space. And what I'll do here, I need to start trying to physically demonstrate things. This front range of chairs, this is my 2 gigabyte virtual address space. So what the cache manager does is it says, this range of my address space, this is what I can use for caching. And then what happens? Let's start walking through the read path. I'm trying to read data from disk. It starts getting really confusing. This is why people say, good luck trying to explain this. I'm trying to read data from disk. The first thing I do when I'm trying to read data is I look over into my cache-managed virtual address space and see, is that data, have I already read it from disk, and have I stored it in memory? If I haven't, then what I have to do is I have to issue a read from the disk. And what I will do is I will read that data into my virtual address space. If I have that data already in my virtual address space, you might think, great, all I do is I copy that data and send it out. But here's where things start getting really weird. And the first time I learned this, it really made my brain hurt, because I'd been used to simpler caching schemes. Even if that data is in my virtual address space, it doesn't actually mean that it's in memory, because that is still just a virtual address. And that's where remember your street cred, that's where comes into play. Because if I had less than 2 gigabytes of actual physical memory to devote to the operating system, MM's job is to go ahead and take things that are in virtual address space and throw them out to disk when it needs physical memory to use it. So I could have this sitting in virtual memory, but it's not actually in the memory of the disk. So what happens is I realize, hey, I've got a virtual copy of that page. I go to read it, and it generates a page fault. I realize that, hey, that data's not here, and I still have to go out to disk and get it. So this really weird thing is going on where CC, the cache manager, actually isn't responsible for maintaining a physical cache, maintaining the data that's actually sitting in memory. All it does is manage a virtual address space. It's the memory manager, that knows how to trim those things, how to throw stuff back to disk, how to read stuff in from disk in order to satisfy that. And then it's the job of the file system to actually retrieve the data from disk and write the data out to disk when CC and determine that it's time to do so. Now, what are the consequences of all of that? Why did I think it was worth this whole digression? The key takeaway is, actually, probably, gentlemen in the audience, the ladies in the audience could have told you this as well. When it comes to performance, it's not the size of your RAM that matters. It's the size of your virtual address space. Okay, I thought that was funny. You guys try to come up with a joke about caching. It's the size of your virtual address space. Since we're limited by that 2 gigabytes, and since only a subset of that 2 gigabytes can be used for caching, as you start throwing more RAM at a machine, especially as you're dealing with today's hardware, you've already run up against the limits. The cache is probably as big as it can get. Now, one of the exciting implications of that, though, is that we are really on the verge of widespread 64-bit computing. When you throw 64 bits at your addresses, suddenly all of those limits go away. Your paged pool size, your virtual cache address size, etc., no practical limits. Paged pool, for instance, goes from about a maximum of, if I remember correctly, around 280 gigabytes of virtual address space 280 megabytes to 561 gigabytes of virtual address space once you go to 64-bit computing. Same with the cache manager. Now, the one other thing, and this is the last bullet here, which is sort of interesting, and one of the reasons why I made everyone take an oath at the beginning. If you read some of our file server tuning documents, they tell you, hey, the file cache trades off with other users of kernel address space, and in particular, the paged pool. So you can go in and you can tweak this key and make the paged pool size smaller than it normally would be, and you would have more space for the file cache. But let me back up a slide. I was telling you here that if you start running into these problems with being able to allocate some of our data structures in paged pool, maybe you want to increase the paged pool size. So we've got some conflicting advice between here and here. And this is one of the key things about whenever you're trying to optimize performance. It's all about making trade-offs. And Windows, for the most part, does try to self-tune, does try to make those trade-offs in the right way for the right workload. And why, if you do have to go in and start making changes to the operating system and changes to some of these parameters, you really want to be careful, because when you increase one thing, you're inevitably decreasing something else that you might need as well. Okay, if the data wasn't in the cache, I have to go fetch it from the file system, get it from disk. Now, what I have here is a diagram of the rest of the disk stack that we'll be talking about as we move closer to where my data actually lives. And let me tell you, first of all, that the areas that I'm going to be focusing on are on the file system. And then when we talk about volume management, I'm going to be spending more time talking about VolSnap, because that's a new component in Windows Server 2003 that's important. Now, I also realized, after I put this slide together, I shouldn't have put FastFat up there at all. Is anyone running FAT on their file servers? Thank you, thank you, thank you. This is another one of those areas where there's a lot of, if you search around on the internet, you can find out facts like that the FAT file system is faster than NTFS. But this is another one of those trade-offs that you just don't want to make. We're going to be talking about in more detail later some of the overhead that NTFS goes through to secure your data and the metadata around it, and trading off that data security for a little bit of speed in certain circumstances is, in my opinion, the exact wrong trade-off to make. So sort of like with the OpLocks, I shouldn't have even mentioned that FastFat was a possibility for a file server. So we're going to be spending most of our time talking about NTFS and then about VolSnap. Okay, NTFS. I think NTFS is really, really cool. I love file systems. Now, one of the cool things about NTFS is that everything in NTFS is a file. I just think that's sort of neat. It just sort of builds itself up from its own internal concepts. You may have heard some of these things talked about before. These are just examples of the NTFS metadata that it keeps around. $MFT is the master file table. That is a file on the disk that contains information about all of the other files on the disk, including itself. How cool is that? What it has is basically a 1 kilobyte data structure that describes the file name, the file security, where the actual data blocks are on disk. The $volume file, that is the volume allocation bitmap. That contains a bit for every cluster on the disk, with the bit set if that cluster is in use, and the bit cleared if the cluster isn't in use. So when you need to grow a file, then we can take a look at the volume allocation bitmap and find the free space on the disk. The $quota file, that's how we implement things like quota. There's some other metadata files like that that implement more advanced features in NTFS. And the last one that's really important is the $log file. This is where we log things in NTFS. Now, this is really, really important, and I want to make sure that everyone who's in this room now understands this and can tell anybody who says otherwise that you might run across in news groups or anything like that. NTFS is a journaling file system. If I had a nickel for every time I heard otherwise on some news group when they're talking about how great some of the new Linux journaling file systems are, I would have, well, probably about $1. But NTFS is a journaling file system. What that means is it has improved reliability for its data and its metadata, and it drastically reduces the need for that dreaded ogre of check disk. But it does have performance implications for metadata operations. Now let me explain what journaling means, and therefore you'll have a better intuition for where it starts affecting things in the operating system. What journaling means, you'll notice that I talked about how everything in NTFS is a file. Now, some of those files contain absolutely critical data. The $MFT, probably the most important thing that NTFS keeps around, because without the $MFT file, you don't know where all of the other files are on disk. Similarly, the $volume file, if you lose information in there or if it gets corrupt, you may think that a block on disk is free when actually a file is using it. There are other structures, like directory structures, which are similarly important, where if you lose an entry in a directory B tree, then the file may be in use and the space may be in use in the $MFT, but you can never find or open that file. So if any corruption happens in any of these data structures, bad things happen, and that's why check disk will occasionally be needed. Now, check disk will recover from a lot of these errors. Now, how do we prevent them in the first place? That's where the $log file comes in. And what we do is the following. It's the same technique that's used in databases. It's called write-ahead logging. What we do, when we're making changes to things like the $MFT file, the $volume file, or to a directory structure, what we do is we write in the $log file a record of everything we're about to do, as well as all of the information we would need to undo that change. And we maintain that in the log file. It's a sequential operation. Now, if this was a database, and by the way, some of those things are grouped together in a transaction. So for instance, if I'm creating a new file, it means I have to add an entry in $MFT, I have to allocate space for the file in $volume, I have to add an entry for the file in a directory structure. And I group all of those things together as a logical transaction. They all have to happen or none of them happen. Then what I do, if this was a database, when I commit that transaction, a database would actually write everything to disk. But NTFS is not a database. It doesn't try to provide the same semantics. All we do is we keep that information around in the log file. And then here's where the magic comes in. And here's where one of the possible sources of problems will come in. CC, remembering your lingo, CC and NTFS have this relationship where, since all of these are files, they can be cached in CC, just like everything else. When I'm making those changes to $MFT and $volume, I'm just making changes somewhere in the cache where those files have been cached. And when MM is getting ready to purge those and say, I need some space, so I've got to write some of that $MFT data out to disk. And CC realizes that, hey, this is actually a special file. It's a $MFT file. CC calls into NTFS and says, I'm about to write one of your key data structures to disk. You better write your log. And that's what NTFS does. It takes its $log file and flushes it to disk first. Then it tells CC that it's done, and then the $MFT file and the $volume file, etc., all of those can be flushed out to disk. So think of what happens when we do this. And the reason why the log had to hit the disk first, that's why it's called write-ahead logging. What it means is that we have recorded on the disk, all the way over here, everything that I'm about to do, how to undo everything that I'm going to do if I have to, and that all gets written out to disk. Now, if there's a crash anywhere in that process, then what happens is, when I recover, I take a look at the log file, and I look to see which transactions were committed. And if I see that a transaction, like a file create, was committed, I have all of the information in that log to redo the operations to the data structures if they didn't hit the disk before the crash did. I can also look for incomplete operations. If I see, for instance, that I was about to make some changes to MFT and $volume, but I didn't commit the transaction, I have all the information in my log file to undo those changes if I need to. And by going through the log, I can bring those data structures up to date. Now, why is that important as you're considering performance of NTFS? It means that there is additional overhead for operations that affect NTFS metadata. If you're just reading or writing from a fixed location on disk, the file already exists, it's the same size, you're just reading information out of it, or you're overwriting sections into it, that's going to be fine. It's going to be fast, performant, no NTFS overhead. But if you're doing things that affect the metadata, create new files, delete files, change the size of files, create hard links, etc., things that would affect one of those key files, then there's going to be a slight overhead because you have to both log the operation and do the operation. Now, this has some implications if you're writing applications that use NTFS. Some of the things that it means are, for instance, that if you're going to write a large file to disk, you're better off if you know the size that the file is going to be, that you go in, set the file size first, and then start writing the data in. Because then that gives you one operation where you're setting the file size instead of having to extend it by little bits along the way. That will be much more efficient because there'll be less logging overhead. Now, there are a couple of NTFS performance considerations that are worth mentioning because these are ones where it's actually, of all of the things that I'll tell you about tweaks, these are probably some of the safest to make on a file server. And it will depend a lot on your application workload that you're using. NTFS has a lot of code in it to try to ensure compatibility with old Windows applications. One of them is 8.3 name creation. In this sense, NTFS is exactly the opposite of the FAT file system. In the FAT file system, those old-style DOS names where you have 8 characters and then 3 characters with a dot in the middle, that's the default for how it stores names, and it has to do some extra tricks to be able to store a long file name. NTFS is the opposite. It can store long file names naturally, and it does some tricks to generate short file names if needed. If you don't have any old Windows applications around that require 8.3 names, you can turn that off. And NTFS will stop generating those. Now, one of the cool things about that is adding an 8.3 name to a file is an operation that has to be logged. It's one of those more expensive metadata operations. So if you don't need these files, then turn that feature off. This, by the way, when we generate those netbench numbers, this is a feature that we disable, 8.3 name creation in our benchmark runs. Another feature that we disable in our benchmark runs is the last access time. By default, when you access a file in NTFS, it's going to update the file metadata saying that the file was accessed at such and such a time. If you're doing a lot of reads from your file server, however, that means you are still updating metadata, writing things to the log file, etc., and you might not need that information at all. So if you don't need a last access time, and note that's different from a last modified time, which we always keep up to date, then you can disable NTFS keeping that information up to date. And when we do our benchmark runs, that's another thing that we do. We disable the last access time. So those two things, one thing that might break if you disable last access time, by the way, is if you have anything like hierarchical storage management, where you're going to be moving data from a disk to tape, for instance, as that data hasn't been accessed in a while. If you disable last access time, you can no longer have those features work. So that's one of the things that you have to keep in mind as you're taking a look at these operations. One last thing that I want to mention about NTFS is and this has to do with file and directory layout. NTFS is much more efficient than the FAT file system in terms of managing directories. The FAT file system just basically keeps its directory as one long list. So when you want to find a file, it has to start at the beginning of the list and start searching through that long list until it finds the file name that you're looking for. NTFS keeps things in a data structure called a B tree, and it can do lookups pretty efficiently. But if you start cramming lots of files into a single directory, then you'll start noticing the performance implications of those extra disk accesses that you have to do to read the directory in. Now, when I start talking about lots of files, where I start getting worried when people talk about it is around the 100,000 to a million file mark in a single directory. If you have 100,000 to a million files in a single directory, you're going to notice the performance slowdown that comes from having to do extra disk reads to find the files that you're interested in. Having lots of files in a single directory affects another thing as well. Oh, didn't want to talk about that. I'll have to come back. I was going to lead into this one, check disk. Now, NTFS is a mature journaling file system, but things can still go wrong. One of the ways where things can go wrong, and we've had to track this down in a number of cases, is where the hardware basically lies to the operating system. I talked about how journaling worked and how, in order for journaling to work, the log has to be written in front of the metadata changes. You have to have write-ahead logging. If the hardware says, okay, I've written the data to disk, but it's still sitting in its disk cache, we can't make that write-ahead guarantee. And a hard power failure, if someone trips on a power cord, that can impact our reliability. It could be that some of our data structures would be corrupt. Or bits could just flip on the hardware. That's increasingly common as disks get bigger. If you just take a constant failure rate for a particular sector and multiply by the increasing number of sectors on a disk, it's getting to the point where chances are something's going to go bad somewhere on a disk within its lifetime. Or it can be an NTFS bug. Those have happened, but that's one of the nice things about having a journaling file system that's been around for about 13 years. So sometimes check disk is needed. Now, we've done a lot in Windows Server 2003 to increase check disk time, but some of the things that can affect check disk time, if you want to minimize how long a check disk would take in a worst case, there are really two important factors. One is the total number of files on your disk, and then the second is the maximum number of files in any one directory on the disk. That's what affects check disk time, not how much data is on the disk. So to flip back, when we're talking about disk sizing, if you're talking about the scalability of a file server, the things that you need to keep in mind. One, how much data do you want to put on that single volume? You really should be thinking about the volume as the unit of failure. What are you going to do if that entire logical volume is toast and you need to restore from a backup tape? Figure out how long you can afford to be down while you're recovering from the backup tape. Figure out how fast you can get data off that tape and do some simple arithmetic, and you'll come out with your maximum volume size that you can allow. For most of our customers, what we're seeing is a common maximum volume size between 200 and 500 gigabytes. And then the other consideration is how many files do you want to put on a single volume? And the key consideration there will be check disk. How long can you afford to be down if a volume requires a check disk to recover from corruption? There's a report from Veritest that will give you some data points about how long it took them to do a check disk on Windows Server 2003 with 1 million files, 3 million files, and I think they went up to 17 million files. I can't remember the details on a single volume, how long it took them to do check disk. So you can take a look at that concrete data and interpolate how long it would take you to complete a check disk. Now, there's one last, actually, really cool check disk point that I want to make, because this is going to be new for Windows Server 2003. It's this last bullet point. It's talking about online check disk file system verification. Why is that important? Well, there are two reasons why it's important. Well, first of all, let me tell you what it means. What it means is we need to have a new tool in the resource kit called Verify Disk. And what that will do is you can run Verify Disk, and it's check disk, but it takes a snapshot of the disk first. See, if you run check disk by itself on a disk where people are writing data to it, you're going to get all sorts of false positives. You can never really tell if the data on that volume is really corrupt or not. But by creating a shadow copy first, giving you a nice clean image of the disk that isn't changing, you can then run check disk against that to determine if there's any corruption. Now, why in the world would I want to do that? Here's the reasons why. First of all, check disk actually runs faster when it's not being run at boot time. So one way to minimize the amount of time it takes to complete a check disk is to not run it at boot time. Now, unfortunately, or fortunately, depending upon how intensively you want to manage your system, Windows is configured by default where if the volume has appeared to be corrupt in the past, when you boot, it's going to run check disk. Now, there's a tool on Windows Server 2003 called CheckNTFS, CHK-NTFS, where you can disable that default behavior. And you can not have Windows run check disk at boot time. You can run perfectly fine with a disk, by the way, where there's 1 or 2 files that are corrupt. Everything else you should be able to access just fine. So you can limp along in this configuration until it's time to actually fix the problem. Now, the other thing, though, is that if you disable boot time check disk and boot time verification, you may have corruption that you don't know about. And that's why Verify Disk is very nice. It's something that you can run periodically to make sure that no corruption has entered the system that you're unaware of. So if you disable boot time check disk, you'll get faster check disk time. The other nice thing about it is you can control when check disk runs. It doesn't have to run when the system reboots. You can wait until the weekend. And then finally, you can use Verify Disk to see if anything has become corrupt. Now, when it's time for me to actually read or write data from the disk, I finally made it to where the data actually lives. In my opinion, one of the coolest features that we've added to Windows Server 2003 is the ability to do shadow copies. Now, that does have performance implications, so I want to make sure that you understand what's going on underneath the covers. Now, first of all, if you don't know what shadow copies are, it's basically a frozen point-in-time image of the disk. It can be used for several purposes. It can be used for backups, or it can be used just to keep that data around, a sort of a poor man's versioning system in case you need to get back to an old copy of the file. Now, how it works is like this. We use a copy-on-write technique implemented in software. The shadow copy infrastructure, by the way, is fully integrated with hardware vendors, so you can get hardware acceleration for some of these. But what I'm going to talk about now is what works out of the box in software. So remember, what I'm trying to do is keep a copy of the original data in case I need to get back to it at a later point. Now, at this point, since we're talking about volumes, I finally made it all the way over to this part of the room. The only thing that I know is block level addressing. I know that the data on the disk is divided up into blocks that are a fixed length, and each of them has a number identifying it. Now, here's what happens. I've created a shadow copy. Now, the way that works is the first thing I do is I call up into NTFS, the volsnap, the shadow copy provider, and gets the volume allocation bitmap, that $volume file that I talked about before. And I get that information so I know which blocks on disk actually have interesting data and which blocks on disk are currently free so that they don't have anything that I particularly care about. I also create a diff area. This is where I'm going to be storing the blocks, the original copies of the blocks as they change. Now, if an application like Word, all the way over there on the client, has issued a write request that comes all the way over here, and I'm trying to write that data to disk, the first thing that the shadow copy provider is going to do is it's going to move an original copy of that block over into the diff area. And then it lets the write proceed. So on the original volume, block number 1 has now been clobbered with the new data that Word tried to write. But I've squirreled away a copy over in the diff area. Another write comes through, and I squirrel away a copy of block 4 and let that get copied over. Now notice what's happened here. I've still got a copy of the original volume as it existed at the beginning of the slide. Just a couple of things have reshuffled around. Now the other thing to notice is that I didn't have to copy all of my data. I'm doing the copies as needed in order to preserve the original image. Now, the shadow copy client, this could be something like a backup application, or it could be something like the little previous versions user interface that we've implemented as an add-on to Windows XP. It's trying to read the disk not as it exists now, but it's trying to read it as it existed at the time when I created the shadow copy. So what's it going to do? If it's trying to read data that hasn't been overwritten yet, then I can just get it from its original spot on disk. And the shadow copy provider knows where that is. But if I try to read data that has been overwritten, then I know to redirect that disk request over into the diff area. Another kind of cool and magical thing is that if I'm trying to overwrite data that has already been copied, I only have to do the copy on write once. So that's an important thing to think about when we talk about the performance implications. And I forgot to put the little demo in there. If I overwrite data that was free at the time that the shadow copy was created, then I don't need to do any copy on write at all. Now, here are the things to think about when we start thinking about the shadow copy performance. First of all, this is sort of a plug for... How many people have deployed shadow copies, like shadow copy for shared folders? About a quarter of you. How many haven't? How many people haven't even heard of it? Okay, if you haven't deployed shadow copies, you really, really, really should. And here are some of the things to keep in mind why you should. First of all, chances are you don't have to do anything except click your mouse 4 times to turn the feature on. There's very little pre-planning that you have to do. If your hardware meets the specs for Windows Server 2003, you can use shadow copies. The impact on the RAM and CPU utilization is negligible from what we found from customers. You can control how much of your disk will be allocated to that diff area. You don't have to do anything to prep your applications or to prep your existing data. It works in clusters. You don't need to worry about an Active Directory rollout. If you have Windows Server 2003, you should take a look at the information available on the File and Print Technology Center. Read up very quickly on what shadow copies do and the benefits they provide you, and just do the 4 clicks to turn it on. What it will buy you, by the way, is the capability to have clients that are running Windows XP or to have help desk that have Windows XP computers recover old or damaged versions of files that have been kept around in a shadow copy. Now, the default configuration for shadow copies would be to take 10% of your disk. You need a minimum of 100 megabytes. And what it's going to be doing is using that information. That's going to be the maximum space that it will ever allow, is 10% of your disk. But it's going to take it as needed. It's going to take a shadow copy of your disk twice a day, Monday through Friday at 7 a.m. and 12 p.m., but you can tweak that schedule. That means that if someone comes in and accidentally deletes a file at 9 o'clock, or accidentally corrupts a file, or accidentally hits save instead of save as to generate a new version of the file, you can go back to either today at 7 o'clock or today at 12 o'clock and get the copy of the file as it existed then. We can't guarantee how many shadow copies you can keep around, but the maximum is 64. Now, this is a performance talk, not a shadow copy talk. So what are the optimizations you should be thinking about if you're deploying shadow copies and you want to have the most performant file server possible? First thing to think about is to have a dedicated disk for the shadow copies. Now, the reason for that is the following. I thought I was done demonstrating things or trying to demonstrate things. I'm over on my disk. It turns out that disk performance really comes down to 2 things. This is the one thing where, I was running back and forth really fast at the beginning, and I was like, sort of silly because you can't make electrons go faster. But with disks, that's actually a physical thing that's spinning in your computer. And that's one of the things where you actually have to take physics into account in terms of disk performance. And it comes down to 2 things. How fast does that disk spin? And how fast do you have to, or how long do you have to wait for the disk head to move over to the appropriate location on the disk? And one of the consequences of that, of the actual physics of hard disks, is that sequential reads and sequential writes are faster than random reads and random writes. Because with a sequential read, I just have to move my disk head over to the appropriate part on the disk and then just let things spin underneath me. If it's random, though, then I have to move the disk head, and that's actual, like when we're talking about electron speeds, actually moving a disk head, the actual physics of making something physical move and then settle down and stop, and then move again and settle down and stop. The difference in performance is astounding. So if you want to optimize disk performance, then you want to make sure that your reads, whenever possible, are sequential, and your writes are sequential. And there's a lot of logic built into the operating system and built into applications that you really don't have to worry about that try to make that work. And shadow copies, if you don't have a dedicated disk, can interfere with that. Because what will happen is you're trying to do a nice sequential write as an application. You get to one block of the disk, And you're like, okay, I'm going to start my write right now. And then what do I have to do? I have to do a copy on write. So I'm like, oh, wait, I'm going to read that data, and I'm going to seek my disk head over, and I'm going to write it into the diff area, and then I'm going to seek back, and I'm going to write the original data down, and then I'm going to write my next block in my nice sequential write. But wait, before I can do that, I have to read it and seek over, and then write it in the diff area, and then seek back and write that block. Back and forth, and I'm going to be ping-ponging the disk head around on the disk. So if you have a very heavily loaded file server, you really want to have a dedicated disk for shadow copies, because what happens then is I come over and I'm starting my sequential write, and I realize, hey, I've got to do a copy on write. But what I do is I read the data, and then on another disk I'm doing a seek to write that data out. My disk head doesn't move over here. So I read the data and then write, and then read the data and then write, and I'm not moving my disk head on this disk. Now, it just so happens that if this is not a heavily loaded server, or actually, even if it is fairly heavily loaded, depending upon your RAID configuration, when we did performance testing on NetBench with shadow copies enabled, it took about a 5% throughput hit. And that was not having a dedicated disk, but this was a RAID configuration where we had 4 spindles available for us to do I/O. Now, if it's a lightly loaded server, or even a moderately loaded server, so our internal servers in OTG, I don't believe have dedicated disks, there's not going to be a noticeable performance hit. But if it's a heavily loaded server, then a dedicated disk is going to buy you some big advantages in performance, and that's a consideration to make. Now, our real-world data around shadow copies, and I'm spending a lot of time on this because this is sort of the new thing about Windows Server 2003. We deployed shadow copies on our 40 file servers that we have in Redmond. 20 of them are used for just sort of My Documents type servers, redirected documents and telemirror scenarios, personal data like Word documents, Excel spreadsheets. They also turned it on web servers. That's something that I actually hadn't considered when I was designing the feature, but they like having the ability to get back to old versions of web content. Another thing that I didn't think about when I designed the feature, this is one of those things where once you start using it, you start realizing all these cool places you can take advantage of this. When they take backups of their databases, what they do is they do a SQL dump to another disk, and then as a separate process, they then copy the data from that disk off to tape. And they're not quite sure how many SQL dump files they can keep around on that disk. So what they've done is they've turned on shadow copies on that dump drive. So then what happens is if they need to get back to a copy of the database from 2 days ago, they might actually have that dump file sitting on disk in a shadow copy, and they don't have to pull out the tape. That's not a scenario I ever would have thought of. But it's working great for them. And then finally, they use this in clustered environments, in a clustered SAN. They've turned it on everything except the C drive. Now, some of the things to consider about with the C drive is that's typically where the operating system page file exists. It gets a lot of random I/O that you don't want shadow copies even in the path at all. They accepted all of our defaults between schedule and diff area allocation. And the bottom line is what's happened to us within Microsoft is that a file restore has gone from a 1 to 3 day operation where we had to go get a tape from the outsourced backup vendor, pay that outsourcing company $150 to get the file back. Something that went through 3 levels of escalation because help desk couldn't request a tape. To something where in 90% of cases, when someone calls into help desk to ask for a file to be restored, help desk can tell the person how to use the shadow copy feature. They have the data back themselves within 5 to 10 minutes, no check written to the outsourcing company. And all of this by taking up to 10% of the drive, just basically slack space that they had sitting around, and no significant impact on their performance. These are some of the real-world metrics. So this is how things were impacting their servers. And this is really just more interesting information for the post-show DVD. So with that said, we're starting to run low on time for this particular session, but I want to make sure we have time for questions. I hope that I went through and gave you a good enough overview of how things are working in a file server for you to understand some of the implications of the things that you can tweak to gain performance. And some of the reasons why you might want to be afraid to tweak things beyond what the operating system does for you yourself. I see some people are starting to leave. before you leave, make sure that you fill out your evaluations. Let us know what worked and what didn't work. This is actually the first time we've done a file server performance talk at any event like this. So it's brand new content for me to present and for you to listen to. You were a guinea pig audience, so give yourselves a round of applause for putting up with me. But that also means that the feedback is going to be especially valuable. I really want to know what you liked to hear, what you didn't know before that you were like, aha, that's sort of interesting. What you thought you didn't need to hear that you knew already or that didn't impact performance. So I'm really particularly interested in the feedback from this session since it is a first-time one. Now, as we start setting things up for questions, you'll notice that there are microphones scattered throughout the room. We've got about 10 minutes, I believe, for questions. I think things are scheduled to end at 12. And, yep. So we've got about 10 minutes for questions at the mics. And after this session, I'm going to go hang out near the cabanas if there are any additional questions. So I'll be near like cabana 12, 13, 14, just probably sitting in a chair somewhere for a couple of hours after this. So that said, I think that, yep, that said, let's hand things over for questions. Thank you.
Are there any plans for actually implementing some kind of clustered file system like the Polyserve Matrix product in the exhibition hall?
So the question was, do we have any plans to implement a clustered file system like Polyserve, which had a booth and a sponsorship here at TechEd? We at Microsoft, we've continually taken a look at clustered file systems. For those who aren't familiar with the lingo, that basically means you have lots of servers that can sort of access data on typically a storage area network where there's no single server that controls where that data lives. We've looked at this market several times, and every time we've looked at it, we realize that it's very important, but for a small set of customers. And Microsoft's strategy is always, let's find the technology that's needed by millions and millions of people. So every time we evaluate it, we come to the same conclusion of, we're glad we have partners like Polyserve who are doing development on the Windows platform to target that need, but it's not something that we expect to build in our operating system. Yes?
When you talked about the shadow copy, that's, at least conceptually, it's nearly identical to what the SAN vendors do with their snapshots and things like that. Now, when you said that you can hardware accelerate them, does that mean I can go get a plug-in from EMC or HP that makes those two things the same?
So what I meant about hardware acceleration with shadow copies is that companies like EMC and HP, as you pointed out, do have snapshot capabilities in their hardware. What our shadow copy infrastructure is for more than just end-user restore. It's also for things like backup and for transporting data around on a SAN. Before the shadow copy infrastructure in Windows Server 2003, the applications had to write basically to EMC's APIs or to HP's APIs to try to control information on the SAN. The way things can work with Windows Server 2003 is you can use the shadow copy APIs basically to control, and this gets back to the short answer to your question was yes. People like EMC and HP have been providing what we call shadow copy providers that plug into our infrastructure, so that you can create a shadow copy and it knows how to control the EMC hardware to do things like split mirrors, move the shadow copy around on a SAN, mount it onto other computers, etc. The end-user restore shadow copies, by the way, that is limited to our software provider. So an EMC shadow copy can't be used for the end-user restore capability, but it can be used for things like a fast backup of a SQL database or Active Directory.
Yeah, that's what I was interested in.
Yep. Yeah, and the end-user restore has to be the software.
Okay, thanks.
We'll go over here now.
Yes, so what's your recommendation on defragging NTFS volumes on RAID 5? Is there any benefit? Is there a necessity to do that?
So the question is, what about defragging NTFS volumes on RAID 5? Is there any benefit? Is there any necessity? We actually have, believe it or not, surprisingly little data about the benefits of defragging disks on various RAID configurations. Most customers don't defrag, which is surprising. So most people, like you're demonstrating you're a more advanced customer to even be asking that sort of question. That's a really long way to say I don't know whether or not it would help you to defrag on RAID 5. We don't study that. A lot of people don't ask.
What do you do at Microsoft with your file servers?
We don't defrag.
Okay, thanks.
You're welcome. Yes?
Is the shadow copy client included in Service Pack 2?
The question was, is the shadow copy client included in Service Pack 2? Not only is it included in Service Pack 2, it's better in Service Pack 2. The reason why is that the downloadable shadow copy client, for those of you who aren't in on the fact, first of all, I used to be the program manager for the feature. That's why I'm so passionate about it. I love the shadow copy feature. We had to develop an add-on pack for Windows XP to enable the user interface. And the way we did that is through a property page. The way you see old versions of files is by right-clicking on the file, going to the properties page, and there would be a previous versions tab if previous versions existed. The problem with that design is that nobody knows to right-click on files, much less click properties. So in Windows XP Service Pack 2, not only is the capability built in, that UI is there, but also if previous versions exist. If you remember on the left-hand pane, it has common tasks that are available for files, like rename this file, copy the file, etc. If previous versions exist, there'll be a little one that says View Previous Versions. You can just click on that, takes you to the built-in user interface. So it's there and it's better. Yes, sir.
You talked about disabling 8.3 and the access times. What kind of performance hit or benefit is there in terms of doing that? Is it large, small?
The question is, what sort of performance hits or benefits do you have in terms of the 8.3 and the last access file? I don't remember the exact numbers, but what I recall is in the single-digit % throughput difference on NetBench. But I don't remember the exact differences. We'll go here.
When 2003 Service Pack 1 comes out with file replication, will that be capable for clustered file servers?
The question was, will replication in Windows Server 2003 Service Pack 1 support file clusters? For those of you who aren't aware of all of the ins and outs of our replication service, you can't replicate from a clustered disk today. And unfortunately, in Service Pack 1, you still can't replicate from a clustered server. And unfortunately, it's even looking like for R2, you won't be able to replicate from a clustered server. But by gosh, Longhorn, that's when the stake's in the ground. But of course, take everything I say about Longhorn with a grain of salt. So unfortunately, Service Pack 1, we still don't have cluster support for replication.
Thanks.
Yes, sir.
We have a volume that's over 1.5 terabytes, and I'm just wondering what kind of slowdown appears that if it gets filled.
So you have a single volume that's over 1.5 terabytes.
Over 4 million files in there.
And 4 million files. How many files in a directory? Do you know off the top of your head? Is it just lots of directories and lots of files?
Yeah, there's maybe hundreds of thousands of files.
Okay.
Directories.
You shouldn't notice a slowdown in your day-to-day performance of that disk. I'm assuming it's got to be NTFS. FAT doesn't go as high as a terabyte. You shouldn't notice any slowdown in the day-to-day performance of that disk, assuming that you don't have an excessive number of files in a particular directory. But at 1.5 terabytes, where I would worry is, what are you going to do if that disk just goes kaput and you have to recover that from tape? It will take, depending upon how fast your tape drive is, it could take quite a while to restore 1.5 terabytes. 4 million files or so also doesn't worry me that much in terms of check disk time. Check disk time would probably, I shouldn't quote numbers because I'm going to get them wrong. So ballpark, though, would be like you'd measure it in minutes to hours instead of days for a check disk of 4 million files. That's not an excessive number to have on a volume. But the 1.5 terabytes, that's what's setting off red flags.
Would it be better if I break it up?
Absolutely. So what I would do, and in fact, if you want to hide that from end users, the fact that you're breaking apart your 1.5 terabyte volume, is this on a SAN?
Yes.
Yeah. What I would do is just go ahead and create a separate logical volume and use NTFS mount points so that you have two volumes, say, of 2 or 3 volumes, say 3 volumes of 500 gigabytes apiece. That puts you back into the normal range from what we see at customers. 3 volumes of 500 gigabytes each, and then use mount points to make it look like one logical directory structure. But in terms of units of failure, it's going to be, if something goes bad on this one volume that's mounted in, you just have to recover that 500 gigabytes instead of the entire 1.5 terabytes. There was a quick question up there. Why not use DFS instead of mount points? You could use DFS as well, but it depends upon how they were sharing that data out to customers. If it's one logical share, You could use DFS or you could use mount points. It depends on if you want things on one server or not. Yes, sir.
On a RAID 5 file server, if you put a dedicated disk in for the shadow copy, is that going to use the whole dedicated disk or just 10% of it? I didn't quite understand that bit.
So the question is, if you have a whole, this is the last question? This is going to be my last question, and then I'm going to start moving over to like Cabana 12, 13, 14, etc. If you have a RAID 5 configuration and you put a dedicated disk, and by that I mean it really should be exposed as a separate volume to the operating system. It would depend upon how you had that configured. The default would be to only use 10% of actually, the math is really weird. The default is you take your RAID 5 volume, take 10% of that, and take that much space on whatever disk you point it at, but it's a simple click in the UI to say, use this whole disk, that it really is dedicated. So, all right, well, thank you all very much. I hope you learned something from this. Please, please, please remember to do your feedback. And my apologies to the AV guys and what I did to their mic.